Okay, dear students, in the last class we have to discuss the Cayley tables of the finite groups, and representing these Cayley tables we identify the inverse and the identity element. And in the last class I have to tell about that the inverse of the elements, each element is a unique, and also the identity element in this table represented by only once in each row in each column. So now we have to, today's lectures we have to discuss the elementary properties of a group. So we have to see what is the group properties. We have to just say that. At the last class we have to starting with the basic things. If we have a set is equal to this is any set of a G, we have a group, and if this is a group we have all the elements are there. So we have this elements. We have to interesting that to show that the identity element because we know the identity element is here. So because this identity element is a unique identity element, we cannot find any other element of this. So that means we have the definition is say that for any E belongs to the G such that there exists element. So for any E composition of A is equal to A and is equal to A into E. So we can say simply that this is the element is a unique, and if we have an element of such element is here, and such element of this is A, and then A inverse is also belong to the same set. So in this case we can say that inverse of the elements is also unique. Identity element is unique for the whole the set, and inverse is unique for each and every element. If inverse of A is B, then inverse of A cannot equal to the C. So this is a unique in the. So we have to discuss the properties of today's lecture, elementary properties of a group. Let us begin with, if G is a group under the certain binary operation, the identity element of a G is unique. This is the first condition, is very important. We have to just say that. Second thing is saying that every element of A has a unique inverse. So we just say that if identity element, then identity element of this set G is a unique, and every element has a unique inverse. And then we have to just say that for every element of A, inverse of A inverse is giving the element itself. And then we have to take for all A and B are the element of a G, then AB inverse is the same as a B inverse and A inverse. So we have to we have to prove all this 4 by 1 by 1. So we have to begin with the first one is we have to prove that the identity element of a G is a unique. Idea is this, we have to prove is very simple, because we have to prove the uniqueness. Proving the uniqueness, we have to take two different identity elements and then show that these both the elements are the same. Let us begin. Suppose E and F are both identity elements of a G. You know that E and F are both the identity element of a G. So if E is the identity element of a G, we can say that simply is E of F is equal to F, because E and F both are the element of a G. If E is working as an identity element, if E is identity element, then E composition F is the same as equal to F, and the same as the F composition E is there. Other way we can say that if F is working as an identity element, then we can say that EF is equal to E, and then we have also EF of E is equal to this thing. So in this case we have to just say that F of E is a working of identity element, EF is equal to F, F of E is equal to F, and if F is working as an identity element, then EF again identity, and this. Now EF is equal to identity, and these two, suppose this is the 1, this is equal to 2. From these two equations we can say that simply say that F is equal to F is equal to, because these two are the same, so we can simply say that EF is equal to F, EF is equal to E, so EF and E. So we take two different identity elements of the group G, E and F, and then both have the same F is equal to E. We have to proving that. So we can simply say prove that the uniqueness of identity means identity of this set is a unique. We cannot find there is a two identity elements in this group is there. Now try to prove the inverse of each element is a unique. So we have to take suppose element A belongs to the set G. Suppose A is the element of a G, and there A has two different identity inverse are there. B and C are the to both inverse of A. If B and C are the inverse of A, then B composition A is equal to identity and C composition A is also identity. So B composition A is equal to identity and AB is also identity, and because B is the inverse of A and at C is the inverse of A means C of A is equal to identity and A of C is equal to identities are there. So we just say that we have to prove that this B and C are the same. So if B of A is equal to identity, C of A is also identity element. So B can be written as a, we just say that B of E, you can write B can be written as a, because E is the identity element of this group G, and B is the inverse of this, means is inverse of this is also belong to the same set G. So B can be written as a B of identity, and now identity can be written as a this identity element we using this A of C. So this identity is equal to A of C. Now using the, because it's a set is a group, so we use the associativity condition BA into C, but BA is again we have identity element, so we put identity and then we have it equal to C. So we have to prove ultimately if B is equal to C, if B and C are both are inverse of A, then B and C are the same, that means both the inverse are the same. So the inverse of each element A has a unique inverse. So in the group every element has a unique inverse. Now second is the inverse of A inverse is equal to identity. This is very trivial because A is the element of a G and A inverse also the element of a G. A inverse is equal to identity and A inverse A is also identity. By the following the definition of a inverse, we can say that if A composition B is equal to identity is equal to B composition A, then we can say that B is equal to A inverse. So we can say that we have to, or A is equal to, we have a B inverse, vice versa. So by this definition we can simply say that if this is identity, this is identity, so we can say that A inverse ka inverse is the same as equal to A is there. So this is trivially we have to proved in this case. Next we have to proved by the third property is we have to just say that A B ka inverse is equal to B inverse A inverse. So I just take a we have to try to prove this A B ka inverse is equal to B inverse A inverse. So we using this property. This property means we take a B composition B inverse A inverse is equal to identity. We have to prove that, and again we have to prove that B inverse A inverse AB is equal to identity. If we prove that AB B inverse A inverse equal to identity, then B inverse A inverse AB is also identity. Then using this identity property of property of this inverse definition of the inverse of a group, we can say that AB ka inverse is equal to B of A inverse. So let us begin with the first one. We have to just taking in the form of this AB B inverse A inverse, because AB all are element AB A B A inverse and B inverse, all the element of a group G. So AB B inverse A inverse, we have to apply the associativity from here. So we have to take A B B inverse A inverse, and B B inverse you know that is equal to identity element. So A identity A inverse, then A inverse is equal to identity elements. Similarly, if we have to try to this other way, B inverse A inverse AB is equal to, we again use the identity element associativity condition, and A inverse A B and A inverse B, we have to take a B inverse, and this is equal to identity element of a B, and this is equal to, we can say that we say that B inverse B is equal to identity element. So we have to prove in the both the cases this is equal to identity element. So if this thing is also identity element, this thing is also identity element. So by the definition of inverse, we can simply say that AB ka inverse is equal to B inverse A inverse. Then all the parts of this results are proof is there. So we using this is the very simple basic properties of a group. Means we have said that the identity element, the whole the group of identity element is unique. Inverse of each and every element is unique, and if we take inverse of a element inverse of a inverse, this element is giving the element itself, and if we take a inverse of a product of a inverse is reversing the order B inverse and A inverse is. Next, in general we have to extend this. We must be very careful about the when we taking A inverse A B ka inverse is equal to B inverse inverse instead of A inverse B inverse. In general we can write A1 A2 AN. This can be reversing the order AN inverse, AN minus 1 inverse and so on is equal to this in the form of this is the remark we can say that. So we must be very careful when we writing the A B ka inverse is equal to, we write B inverse inverse, not A inverse and B inverse. This is not a true is this form. Let's another example remark is saying that a to the power 0 is giving you a, simply we say that identity for a positive integer k, a to the power k is written as a dot a dot a. We have a k times of a in the form of this, and from the 1 we have to take a inverse. So a k ka we take a inverse of this. This means we have to reversing the a inverse, a inverse, a inverse. Again this is a k times. So we can say that this is again is a k times. This means this can be written as a inverse to the power k, or we can say that a to the power minus k. So the element of in the general form a k to the power inverse is the same as you will denote it as a this form a to the power minus k, because this is giving you have a all this thing is equal to this can written as a inverse to the power k, and generally we denote it by a to the power minus k is there in this form. So this is the remark. Now we have to just say that we have to prove that a b ka inverse is equal to b inverse a inverse, but in general if we take a b ka power minus 2, then b is not equal to b to the power minus 2, a to the power minus 2. For example, that is we take a two different elements. For example, we take a group of a GL2R. The group of all invertible matrices where determinant of A is not equal to 0 and determinant of B is not equal to 0. We take A is equal to this matrix and B is equal to, we taking this matrix 0, minus 1 and 1, and clearly A is the element of a GL2R and B is also the element of this GL2 R is there. We say determinant of A is not equal to 0, determinant of B is not equal to 0. This means clearly these two are the invertible matrices are there. So we take the A square is simply we take a square is equal to take a product of this. We have to like this 1 minus 2 minus 1 1, and then we have to 1 minus 2 minus 1 1. If we take into this is equal to 1, and you have a plus 2 is equal to you have a 3, and similarly we have to take as is equal to minus, I just take a write into the, so we just write into this form. This is equal to 1 and minus 2 is equal to 3. Then we have a minus 2 and minus 2. So we have a minus 2 is equal to minus 4. And then similarly we have to, this is equal to minus 1 minus 2. And this is a minus 2 and plus minus plus 2 and plus equal to 3. Similarly for a b square we have to calculating b square is equal to this matrix is coming into this form, and you can see we take a inverse of this. Inverse of this is simply is a take a inverse of this. We can a to the power, simply we just say that a to the power minus 2 is equal to a inverse ka square, or yeah we can say that a square ka inverse. So if we take inverse of this matrix, we have to 3 by 2, and then you can say that inverse of this into this form, determinant is equal to 1. So you just dividing this. So a is inverse of this is equal to this matrix, and inverse of this is equal to this matrix is there. So a to the power minus 2 is equal to this, a to the power minus b to the power minus 2 is equal to this form. So now you see we have to just say we have to trying this, we have to show that a b ka minus 2 is not equal to b to the power minus 2, a to the power minus 2. So we have to calculating the product of a b. So we have to ab is equal to, we have to clearly is equal to this form. Now take a square of this matrix, we have to ab square is equal to, we have to this matrix we have to coming into the after taking the square. And if we take inverse of this, again we have a 7 into 7, and then you have a 12 and plus 4, and this a to the power. And now you can see if we have a this matrix, now we have to calculating the this matrix is equal to b to the power minus 2 and a to the power minus 2. So thus b to the power 2 minus a to the power minus 2, we take a product of these two. So we have take a product of this 2 1 1 1, and then we have 3 4 2 3, and that much is equal to, you have this form 3 to the 6 plus 3 to the 6 plus 2 is equal to 8, and that is equal to 7, and then similarly these two matrices are not equal. So in general we can say that AB ka in general this we have a AB ka power inverse is equal to B inverse A inverse, but in general this A to the power, this is not true. We have a provide a counter example for this. A is equal to, if this matrix or the B is equal to, they are the elements of a group GL2R, where is the element. So this is not a satisfying into this form. Next properties of a group is very important. We have to using many times as a cancellation law hold. In a group, the cancellation law is a hold. The cancellation law is saying that G be a group with the binary operation, whatever binary operation we have to using, and A, B, C are the element of a G. If AB is equal to AC or BA is equal to CA, then we can say that B and C are the same. Yani ki we can say that if AB is equal to AC, then we have to cancel the left side for A and getting the B is equal to C, and BA is equal to CA, then again the right hand side A we have to cancel out, cancel the right hand side, and B is equal to C. So this means cancellation law is hold for all groups. We have to just say that. So we have to just give the proof of this. Simply if we have a AB is equal to AC is there, so we take a we have A and B are the element of a G. So every element of a G is a group. Every element has an inverse is exists. So we have to just say that AB is equal to AC are there. So if AB is equal to AC are there, so the inverse of this element is exists. So we have to multiply from this. AB is equal to A inverse AC. Now using the associativity condition, B is equal to A inverse A over C, and now A inverse A is equal to identity of B is equal to identity of a C, and this implies that identity of a B is equal to B and identity of a C is equal to C. So we can say that B is equal to C ultimately. Similarly, for the case of this, BA is equal to CA, then we have to A is the element of a G, then A inverse is also the element of a G. So we can write BA, A inverse is the same as a CA, A inverse, then V of A associativity condition, we can say the C of A inverse, and then we can say that this is equal to B identity element, C identity element, then this is equal to B of C is there. So cancellation law in the group is hold. Either we can just say that if we have multiplied this and then we have to getting into a this form. So B and C are the, we have to proving the same. Similar for this we have to from into this form is there. This is the another result we have to proving that if A and B in a element of a group, then the equation Ax is equal to B and Y is equal to B have a unique solution for X and Y. So means we can say that if elements of a groups are there, Ax is equal to B, then X is a unique solution in a group G, and Y is equal to B, then Y is a unique solution of a in G. So let us try to prove this results by suppose we have to say Ax is equal to B and A and B are the element of a G. So we have to just say that this implies that A inverse Ax is equal to, we write, because A is the element of a G. So if G is a group, then A inverse also is the element of a G. We know that every element has an inverse in the group. So if A is the element of a G, then A inverse is also the element of a G. We multiply it from the left side with by A inverse. So A inverse AX is equal to A inverse B, and now using the associativity condition here, we can say that A inverse AX is equal to A inverse B, and this is giving you identity element, and this implies that EX is equal to A inverse B and EX is equal to A, and now X is equal to A inverse B. Now we have to just show that if AX, this is a solution for AX B, now we have to show that this is a unique solution. And the first part of this proposition is clearly say that we have a solution Ax agar B hai, there is a solution X is equal to A inverse B is a solution of this equation, X is a solution of AXB. Now because he say that this have a unique solution, so now we have to show that the uniqueness. Suppose we have a this has a two solutions, suppose let x1 and x2 be two solution of the equations Ax is equal to B. If x and x1 and x2 are the two solutions of this equation Ax is equal to B, then A of x1 is equal to B, A of x2 is equal to B, then trivially this satisfy this. And if Ax1 is equal to B, then x1 can be written in the form of a so this means all the same. This means this implies that Ax1 is equal to Ax2, and by the cancellation law we can say that by the cancellation law Ax1 is equal to B, Ax2 is also the B, so both are the same as this form. So we can say that Ax1 is equal to Ax2. If Ax1 is equal to X2, this means we have to applying the cancellation law here, then we getting x1 is equal to x2. That means if the solution of this equations is a unique solution exists. Similarly, if we have to prove that if y A is equal to B, so y is equal to B, A inverse is a solution of a y is equal to B, and again that solution is a unique if there is exists two different solution of in this case. So we can easily prove that that is equal to the solution of this A and B. This is the equations are solution and their solutions are unique. Let's example we have to just say that find the solutions of this this proposition. G be a group, we have to already prove that this G quaternion is a group, and with the condition of I square j square k square is equal to -1, and I and I j and ji not equal to same, the ij is equal to k and ji is equal to -k is there. Suppose x square is equal to -1 and that is equal to 6 solutions, namely we have a x is equal to plus minus I, so you have I square is equal to -1, minus I square is equal to -1, j square, k square, all are satisfy this equation. So there is x is equal to, we have a total is a 6 solution. These are the. Similarly, if we take x to the power 4 is equal to identity, then they have a we have a has an 8 solution. In fact, every element of a G has a solution. We have a total 8 elements, so plus minus 1, plus minus I, plus minus j, plus minus k. These are all the possible solutions are there. So this means x to the power 4 is equal to 1 to the power 4 is equal to identity. I square is equal to, you know that this means I square is equal to -1, then you have a I to the power 3 is equal to -I, and I to the power 4 is equal to, you have a 1 is there. So similarly you can say that I to the power 4 is equal to 1, j to the power 4 is equal to 1, minus I to the power 4 is equal to 1, minus j to the power 4 is equal to 1, and then similarly we have a k to the power 4 is equal to identity, minus k to the power 4 is equal to identity. So if equation has x to the power 4 is equal to 1, then in this quaternion group we have a total 8 solution of this. So this is the example for we have a previous proposition which saying that if Ax is equal to B, it has a solution, and that solutions are the unique solution. Now we introduce the concept of a integral exponents of the elements in a group. Let n be a, this n be a n is z, belong to the z, and g is a under binary operation is star, be a group, and let g is the element of a g, So Gn can be representing in the form of a G binary operation, this when n is greater than equal to 0, then G inverse when n is less than equal to 0, and whenever n is equal to 0 we have to representing as a identities. Where the first case we have to just say that n copies of G, and the second case we have in the product, and the second there is a minus n copies of a G inverse, and then so this is minus n copies are the G inverse, so this means G to the power n can be written as a G to the power minus n to the power minus. So minus n copies of a, these are the minus n copies, and these are the n copies are there. So if minus n copies are the G to the power n can be represented as a G inverse to the power minus n, because n is less than equal to 0. So this we representing of this set into the form of a into G represented into the form of a this Gn, and then we have to state a theorem in regarding this internal exponents. I am not going to prove this theorem, but we have to using this result. This is called as the exponents law. Is saying that if G, let G be a group, and G and H are the element of a G, and Ij are the element of a Z, then G identity is equal to G inverse to the power minus as minus copies of a G inverse, and then G minus I to the power minus I we can report in the form. And if G to the power I is the same as, we can say that G to the power I, G to the j is equal to G of I plus j, G to the power ij is equal to G to the power ij, G inverse H J power j is equal to G to the power inverse H to the power j and G, and then we have to, if GH is equal to HG, then we have to do G to the power j H to the power j, H to the power H to the power I, H to the power I, and G to the power j. If GH this, then GH whole to the power I is equal to G to the power I and H to the power I. These are the exponents law. No, this is, I am not going to prove here this exponents law, but we have to try to using this exponents laws in the we have when we using the some solve in the problems is there. I have to stop here this lecture today. We have to discuss the elementary properties of a group, and in the next class we try to solve some problems of the groups using this elementary properties and the definition of a group, and after that we have to move further for another things as a like the subgroups, all this thing. So now I have to stop today lectures here. I think you have a clear everything about the properties. This we have to proving certain properties of a group. So thank you very much.